Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. Alright, so in this video we're going to finalize the modeling process of this lattice steel tower, and I'm gonna very quickly do that. Of course, for the people who are watching this for the first time, this is the fourth part of a previous three-parter. In part one I've explained what transmission towers are and how they are basically thought of. Part two was about modeling, but I stopped here because we needed to talk a little bit about loads, which was done in part three. So now we're going to finish the modeling in this part. So according to my dear subscriber, Donald Khanier, there was a request that we want to basically do a quick recap for the loads calculations for this. Now, please notice that I'm going to do massive simplifications here, but I think this is granted because, or warranted, because I've already explained in painstaking detail how loads are actually calculated. Also, I don't want to go into details, for example, in calculating wind loads, because I want to try make this video series as code independent as possible. However, sometimes I will have to rely on codes just to prove some of my assumptions if there is need be. So for now, I will assume that my wind pressure is 1 kilonewton per meter square. And for the wind span and the angle and the weight span, you can find this in page 2062 of the AJICA report that I've uploaded before. You can see that I've taken those values from here. Of course, I'm now using this tower to design. Of course, you have other towers which you need to design, but I'm going to stick for this type of tower. And you can see that 450, 700, and 2 degrees. If you look on the Excel sheet, you can see those just fine. Also, you need the cables, and to find those cables as well, you go to the documents basically, and you can find those on the page 35 of that said document. Of course, I need to rotate again, and you can see that I basically, remember this is a simplification, I basically used the diameter, used the nominal weight, which is going to be used to calculate the self weight of the cable, and use the tensile strength, ultimate tensile strength in kilonewton. Now, of course, one of you could say, well, this is an ultimate tensile strength, but on the working conditions, the cable is not going to have this tensile strength. Upon which I say, yes, you are right. Under working conditions, the tensile strength or the tensile force in the cable is going to be much lower than this because of factors of safety and environmental conditions. And I want to add to this that actually the tension inside the cable is not a number that you can use as a constant. However, it depends on its elastic modulus and the current temperature and the thermal expansion coefficient and lots of other kind of stuff. However, because I want to be on the safe side and I want nothing of this entire environmental discussion here, I'll go to the ultimate tensile strength, as in I'm assuming the cable is under the maximum load, which should give you a better or more safe structure. So I just took the ultimate tension, put it here, and the weight per unit length is also given. Also, the insulator assembly assumption is 1 kilonewton. This is in line with the reference I've shown you that he's assuming insulator assembly loads. The structure was done using L shapes. You remember that I've used L shapes to model the cross-section of the structure. And of course, if you have an L shape and you apply wind loads to those L shapes, then you will have pressure on that L shape, which will become a force when you multiply it by the width of the L shape. So I'm assuming that the side distance of this main element is 25 centimeters, and for the secondary elements, it's 15 centimeters. This is a gross, inaccurate assumption, but remember, I don't want to go into details of calculating wind loads, so I'm doing this very simplification here. Now, truth to be said, it matters how the orientation is of those legs, but remember, I'm using a very simple simplification for the wind loads for now. And my point here is, I want to teach you how to model and design lattice steel structures using basically common engineering knowledge. Whenever there is code specifics, I would just quickly run through them. So please pardon that, and I hope that you don't mind. Now, one of you could say, well, this is a gross simplification of the matter. Like, why are you doing this? Why aren't you showing the full calculation steps? Upon which I reply, well, you have a reference that shows the full calculation steps, and you can check the reference if you are interested in finding out the entire areas and how it's calculated. It's a long story because I want to focus on the tower right now. I will leave the interested reader this material to read. It's actually uploaded and you can check it out. It's, I think, linked in the previous video, which was about load calculation. All right, fantastic. So now I have everything I want. Let's calculate us some loads. So let's just run through this basically tutorial very quickly. You can see that one of the most important things that are calculated are the vertical or the transverse and vertical loads of the cables as well as the tower. So the cable is quite simple. You have transversal, you have vertical loads, which are going to be the weights of the cable. So I'll say weight of full cable. Well, it equals the entire weight span multiplied by the length per weight per unit length. Of course, this is in kilograms, so I need to multiply by 9.81, and this gives you the total weight in kilonewtons. Of course, sorry, I mean in newtons. Of course, this weight is not fully carried by the tower because you have towers beside each other. So half of the cable is carried from one tower and the other half is carried on the other tower, which means half plus half equals 1. This is the weight on the tower due to cable. So I'd say here this is called VL to abide by the terminology written in the reference. Of course, here I'm going to say working conditions because there is something called the failure containment condition. Furthermore, you have a transversal load T, and this transversal load is basically due to wind loads. Now, of course, I'm going to multiply the wind load. How do I do that? Well, you need a side area multiplied by the pressure. So pressure multiplied by the side area. What's the side area? Well, it's the conductor diameter, of course, divided by 1,000 to get it to meters, multiplied by the wingspan, which is 450, and multiplied by the pressure. So this gives you, let's see, pressure, width, height. This gives you the total load in kilonewtons. Please notice the difference in units because here I'm assuming kilonewtons. This is extremely important to notice. Okay, so far so good. It seems to be small. Let me just double check that. Okay, 450. Yeah, the conductor is small. Wait, let me just check something. Is it given as the diameter of one piece or the bundle? Okay, of the bundle. Just for the listener, I'm double checking if this is the diameter of a bundle or not, and it is the diameter of the bundle. You can see the individual diameters here, and this is the diameter of the bundle because I was thinking maybe I am taking the diameter of one cable, but I was wrong. It's all good so far. Okay, so that's the transversal loads due to the wind loads. Finally, I have something called the inline angle loads because you have inline angles, so there is forces because of that, and those forces depend on the angle you have, and you can see them here because remember the transversal forces are partially wind and partially the line angle. I'm assuming now that the wind is in the direction of the line angle, so I'll just call this TW, and I'll call this T tension, TT, and here I would say that the load here is going to equal, well, you are still not in the failure containment mode, so you have two cables now. So each cable will pull in the direction of the wind using the cosine and sine. Now, you are assuming that the line is parallel, and this, by the way, the details here is something that I've explained in the previous video. I'm just very quickly reiterating. So here this equals the tension inside the cable multiplied by 2 because you have two cables, don't have the failure containment, multiplied by sine. And here you need to pay attention in Excel that you have to radian your angles. So you click on the angle, multiply by 3.1415, which is pi, divided by 180 to get it in radians. You have the tension of the cable in the direction of the wind. So now you have, this is wind, and this is tension. I'll call this own weight because tension is from own weight. So I think this is dead load, and this is dead load. It's important to know, and this is where things were strange for me. Here you see that this is added together like this, but I think it shouldn't. My personal take on it is that you have wind load, which is a different case than dead load, so you should separate them because you have cases of loading. This is where I don't agree with the ASCE. I don't know. Tell me your thoughts. I personally think that I am more safe if I do this. Feel free to tell me in the comment section what you think about. I think that I should split the wind and the tension. So thank you, my dear subscriber Donald Khania. You actually let me see something while I'm applying them instead of lazily doing some numbers. Okay, so Now, I also want to go to the failure containment very quickly. So, of course, there are multiple cases, but I want to go to the failure containment just to show you two cases that are calculated. You can see in the failure containment, you have a broken wire. And since you have a broken wire, of course, I'm not talking about gravity wires, or I'm not talking about ground wires. I'm talking about the broken suspended wire. But you can see that he's multiplying this by 1,800 over 2, so he's multiplying this by half of self weight. How do I do that? Well, I go here. Once again, to the vertical load, it was calculated by this. I think I forgot the insulator assembly, right? Yeah, I think I forgot that. So I should say here you have insulator assembly to add this, and I would say here this equals 1,000, so 1. This is of course kilonewtons. And now if I say here the failure containment, it becomes an easy task, because in the failure containment I have only, I can copy this very quickly like this, paste it here, and yeah, I'd say here my vertical loads of the cable is going to be half of this, because it's only one cable. In wind I don't have wind, I'll zero this. In the T tension, I'm assuming that I have only one cable. I'm basically going to say this equals half of the tension in the cable, because one of them got broken. The insulator assembly is going to be still a 1 kilonewton force, because it doesn't matter if a cable gets broken, the insulator assembly is still there, assuming. Please notice that here the code seems to use some RSL factor to multiply this by 0.7. I will just multiply this by 1 because I want to be on the safe side. Finally, you have now a horizontal tension in the cable that is going to basically move the tower parallel to the cable, and this is a new force. I'll call this. I think this is called as L. Yes, it calls it L. So here I'll just call this L, and this, or TL. This is now the tension in the cable, but not multiplied by sine, in cosine. Previously you hadn't had this because the cables were balancing each other out. Now you have it. So I'll just basically take this, copy it here, paste it here, the equation, and just change this to cosine. So of course no 2, they don't multiply by 2 because I have only one cable. So I delete that, and this is in, let me just check what I did. So B9, which is my ultimate tension in kilonewtons, multiplied by cosine theta over 2. So yeah, I should have put here. Now remember, this theta is split into 2. Each line gets 1 theta. So if my real theta is 2, I should put a 1 here to make it correct. So yeah, I think that's right. So far so good. This is in kilonewtons. And now I'm ready. Notice that well, not all cables might have failed, but I'm assuming the worst case scenario, I'll assume that all the cables have failed. Now I have my loads and I can start applying those loads. So okay, let's go to Robot and start applying those loads. A good thing here is just to take this and divide by 1,000 to unify my loads to kilonewtons. So this is a kilonewton now, and this is a kilonewton too. So now I can start doing my stuff. So okay, I'll go to Robot now. And those are huge loads, to be honest. I'm surprised. 4,000 kilonewton, that is immense. Anyway, I think, let me just double check. I just have a bad feeling about this. So B4 is my weight. Is it really that much? Am I doing it right? Now, this is where I keep second guessing myself, but it's a good thing actually. See? Now, once again, I'm not going to video edit this because I want you to see that. You see, I had the feeling that this is just, no, like this is too much. And I was right, this is too much because like 4,000 kilonewton, and I'm not embarrassed to tell you that this is too much. I'm not embarrassed to tell you that I messed up. You see here, this force, 4,000 kilonewtons, is just large, and I just don't accept that. This is too much. And you see, I fell for this little trick, this unit trick. You see, 602 kilograms per kilometer is just way too much here. And you see, this is a kilometer, not a meter. So, well, I messed up. The idea here is that I should put a 0.602. Yeah, now it makes sense. Now it's a normal force that I can live with. Yeah, sorry about this, but, well, once again, I want, as my dear subscriber said, I want to keep it real, and I want you to see the thought process and see where you can, well, catch yourself, because I mean, look, the numbers were all out of the charts. You can see 7, 2, and 4,000. Like, how does this even fit? So, yeah, I kept second guessing myself, and it turned out to be working. All right, so now I'm happy. Now it makes sense to me. So let's go to robot. Click on the force. Now I need to basically very quickly derive me some cases here. I'll call this dead and call this wind. I'll add the wind here, and I will open me another case, which is going to be dead load 2. This is for the failure containment. And another wind load. No, there is no wind load for failure containment 2. So dead load here. I can actually rename it if I want to say here to FC, as in failure containment. I didn't add wind load because there is no wind load in the FC, right? Let me just check. Yeah, there is no wind load. So, okay, I have those cases. So now let's start applying our forces. So, of course, in the FC, now, strangely, robot doesn't apply self-weights unless for the first dead load. Let me just quickly check. Okay, show me the load. Yeah, see, in dead load 1, there is PZ, which is the own weight. If you go to FC, there is no PZ. Now, you should have PZ. You should have dead loads, own weights. How do you do this? You go to self-weight, click on add, and you can see that magically it has the self-weight. All right, fantastic. So going on with this, now we want to apply those loads into our model. So let's take a look first of all. So my robot here has, as I said, 2 anchor points, which means now this is different from the report here. The report here has 1 anchor point where you add your cables. However, I opted for 2 anchor points because it's easy for implementation. Now you could say that this will increase the material cost, and you might be right. However, if you have 2 anchor points, you can split your forces into 2, and this might cause cost savings in this truss. This tower doesn't care. It doesn't matter if it's 1 anchor point or 2 anchor points, truth to be said. However, for this truss, I think that it does matter if you have 1 anchor point or 2 anchor points. So I'll leave it as 2. Okay, so whatever I have force here, I will divide by 2, basically. I did this, but I will just, because you have some forces, you have 2 anchor points, so you have division by 2 for those forces, which is something I have done. Now, we have opened the 3 cases here, which is dead load, wind load, and failure containment load. So let's continue. So now I need to know what the dead load in the horizontal is, or in the vertical is, and what the dead load in the horizontal is, and what the wind load in the horizontal is. I need to know those things because I want to add them together. So let's take a look. Now, this is VL, which is the vertical load of the cable due to the weight. So this is a vertical load. This equals this. Now, TW is transverse due to wind, and TT is transverse due to tension in the cable, which is not the case. So those are my vertical loads. Now, what about the horizontal loads in dead? The horizontal loads in dead are the tension in the cable in dead, and the wind load is basically the wind load tension, basically. I think that's everything. Now, of course, you can drag this down to get the same results here. The same thing applies here. The dead load vertical are going to equal to the vertical of the cable plus the vertical of the insulate assembly. Now for dead load horizontal, here the things get spicy because you have 2 dead load horizontals, because you have dead load horizontal in L and you have dead load horizontal in T, because you have dead load horizontal in the direction of the line, which is due to the failure containment. This is really tricky. You need to pay attention here. And you have horizontal dead load transversal in the direction of the wind, which is due to the tension here, which is what we want. So I'll add this. Finally, you have the wind horizontal here. This is 0. So I'll basically take this, drag it down. Now I have to pay really good attention when I apply the loads because this is a nightmare. So, okay, I go to robot. Let's take a look. My dead load vertical is 5.1, so let's make it 5.5. So I go to my load, select here, say 5.5 in the Z, and basically select my node. So I'll add that. With some more node magic, I'll select this, control, select this. It doesn't select, right? Again, select this. I think I have everything. Do I? Well, only one way to find out. So apply. Yeah, I have them. Perfect. Now those are the vertical forces on the nodes. I will keep them selected because I want to add the dead load horizontal. And dead load horizontal is 2.02. I will assume it's in the positive x, so 2.02 positive x. I'll add that. So now it should apply. It's dead, right? Yes, it's dead. So I should apply 2.02. Let's take a look. Yes, it did. Now I need to yet again apply another load in the wind load case. Here, I'll apply another load. I keep my node selected so far. I want to apply 7.43, so 7.5 kilonewtons wind load. I'd add this and apply. Yes, I have my loads. Perfect. So now I have my loads for the wind load for the normal case. But what about the failure containment case? On the failure containment case, I have a different set of loads. So let's do that. My nodes are still selected. No need to select them again. So what do I have? I have dead load vertical, which is 3.06. It seems to be less because, well, there is one cable that died. So let's add that, apply, and you have my 3.1. Nice. So going on, I have no wind load. I have dead load in the direction of the line and dead load in the direction of the wind. So let's do the direction wind dead load. So this is 0 now. I said my wind direction is X, so 1.01. Let's add that. Apply here. I forgot to increase it, so no problem. I'll leave it as is. And then I have dead load in the longitudinal direction. So how do I do that? I go here, do this to 0, and apply here a force in the Y direction. So in the Y direction is 58, so 58. That's right. Is it right? It's not right. By the way, I messed up. I forgot that I should divide my forces by 2, but there is a very quick fix for this. No problem. I didn't intentionally do this, but I will show you the quick fix. So I was using those forces, although I calculated the halves here. No problem, I can fix that. So going on with this, it's 58, so fine, 58. I'll add this, and now I have all my forces. Now remember, I messed up my forces because I forgot to divide by 2, although I have 2 anchor points. So how do I do that? Well, it's very easy. You go to loads, load table, you check out your load values and basically override them. Well, let's take a look. If you look here, you have 5.5. This is going to be 2.25. You have here 2.02. This becomes 1.01. You have here 7.5, so this becomes 3.75. And you have 3.1 here. This becomes, I don't know, 1.55, I think, 1.55. And this was 1.01. Why? Okay, there we go. Yeah, so it becomes 0.50 something. 0.505. This was 58. And because I have 2 connection points, I'll assume it's each of one is the half. Should be 29 if my calculations are correct. Yeah, okay, seems to be fine. So I'll save that. And let's take a look. Yes, my forces got fixed. Perfect, fantastic. So those are the forces. Now, I still have one force here. It depends if you have actually a cable here. I will assume I have. So I'll go here very quickly and repeat my entire process all over again. So, well, what do? I have one node, so no need to divide by 2. Yes, it's working. Perfect. Okay, so now I have my loads. Finally. Let's run the analysis now, hoping that everything is fine. Of course, my tower is going to look strange because it's not deflecting. Wow, that is bad. That is really bad. Like you have 14 millimeters of deflection. This is... Wait, what? Really? Only 14 millimeters? No, that's not bad. Okay. Oh, that's beautiful. Look, I was looking dead load. I was puzzled because the tower also leans in the dead load, but the reason behind this is because you have tension in the cable. Remember, the cable has a line angle, and the line angle is what makes the tower lean. Of course, this is 3 millimeters, but it's exaggerated because of the deflection thing. And of course, if you go to the wind, it goes all over the place. Now, this is a lie because you will have to normalize your deflection. So you go to loads, no, you go to results, diagrams for members, and with deformation, normalize that stuff, and now you're still 14, but at least it's not shocking. I'm really interested in seeing this. Okay, this is the failure containment, and this is beautiful because look, in the failure containment, you have tensions from one side. The tower is being pulled to the other side because there's only cables from one side attached to the tower, and this side is empty, and that's why it gets pulled to the side, which is beautiful to say the least. Okay, so I think that our laws are correct, but we're not finished. The final thing in the modeling department here is to release our truss members. And here I had a nice discussion with my dear subscriber Nisapa. It just was talking about how trusses could look like in 3D. So, well, let me just put here 2 members. And let's run the analysis now. And everything seems to be fine. So far, so good. Now, of course, those members will have bending moment diagrams because those are beams. So if you click on bending moment diagram and go to view, you can see the normal bending moment diagram that you are used to see. So far, so good. Now, you can still go to geometry releases and, well, you can release in pin here. This could still cause instabilities, I think. Now, regardless of the instability now, it will cause instability because of the torsional possibility here. So I run it anyway. It will cause instabilities, I know, but never mind. I'll just ignore it for now. You can see the simply supported moments now because you released this. Now there is one extra thing I didn't talk about. In the properties, you can actually, first of all, I need to remove the releases. So let me remove the releases first. So let me just delete the release here. No release. And no release here. So if you run the analysis now, you should see the normal moment that you're expecting. So far, so good. Now, there's one cool feature in Robot. When you go to geometry, there's something called, I think, properties. I'm trying to remember. Additional attributes, yes. And you can force it in the advanced member properties. You can force it now to become a truss member. And you will be surprised. So let me just click here on truss member without tension compression. So I wanted to calculate both. And I'll add this to those two guys. So I basically click here and make this become a truss. Click here, make this become a truss. And if you run the analysis, if you go to results, diagrams for members, you see no moment diagram. You see no shear force diagram, which is odd. But the cool thing about this is that if you go to reactions, you can see that there are some reactions, which means that the suggestion I suggested to my dear colleagues to take the load and divide by 2 is actually done by robot. So if you go or if you create a truss member by going to truss members in the advanced geometry here, additional attributes, it will force a truss member even if you have WL square over 8 self-weight, which is a cool feature. And well, I will use that. So let's go back to our structure. All right, fantastic. Now, the first things first, you need to always have an eye on what do you want to release and truss and what you don't want to release. You see, I want those codes to be one continuous piece. I also want those things to be one continuous piece. So my assumption, and this is very important, you need to, and I keep saying this in every steel structure, uh, problem, that connections need to be planned. So now I'm planning that I will keep this as one piece and bolt those elements to them. So how can I do that? Well, you need to keep this in one piece, so don't trust this, just trust those diagonals. Now, how can you do this? Well, of course, it will take some time. Allow me to show you some. So first of all, I will run the analysis, and I will show the moment diagram very quickly. So, well, where's my mouse? Results, diagrams for members, MY. So obviously my members have moment diagrams, as you can see. They have all moment diagrams. So now I want to start eliminating those moment diagrams. I will make trusses and truss members. So for the standing ones here, I will assume that, well, I think I was smart enough to split my sections, right? Let me just quickly check. I planned ahead. I remember I planned ahead, but I think I messed up in the very end. So no problem. Let's do it very quickly. This is gonna take all day long, right? In my planning phase, I didn't plan perfectly, so now it's back to bite me. So I'll just quickly video edit this. I mean, what I'm gonna do is I'm gonna select those members and apply a truss member to them. Of course, this takes time, so I'll video edit this very quickly. Okay, it took me some time, but I think I have grouped them together to ease the access to them. So I go to geometry, additional attributes, and basically make them become truss members to carry tension and compression. I apply that, and I have trusses all over the place. Now, of course, there was one thing I forgot to do in the wind load. Now, of course, before I start, you have wind loads here. Now, I will leave it for you because there is a wind load on the structure, and you can calculate the wind load on each and every member and apply it. Run the analysis now. It should still be stable. It is stable. And, moment diagrams should be acceptable for those members. So I'll just go to results, diagrams for members, MY, apply. And if you remove the section, you can see that those are truss members. Those are dead. They only have axial forces, which is the case. Okay, fantastic. Are we finished? No, of course not. We have still more truss members to talk about. So now for those two things, and this is where the science is. You need to know how those are in real life. So in real life, I'm gonna assume that this element is a continuous element and the rest are trusses being connected to them. I mean, look, I could be lazy and just run the analysis and look cool, which is still gonna impress the viewer, but that's not why I'm here. I'm not here to look cool, and that's why I keep my errors for you to see. I'm here to make you understand, not to look cool. So I just create a group out of the selection. I think I have it now, so I just double check. I hope I didn't mess up. Yeah, okay, perfect. And I'm gonna trust those guys. So geometry, advanced parameter properties, and please trust them to carry both tension and compression. If I run the analysis now, I think it will still be stable. And I think I'm done with my analysis. Please notice, very important, I have not applied wind loads on the structure. This is something I will leave for you. However, I think the structure makes sense so far, and I think we are ready to design the structure. Please keep in mind that I did not apply a wind load yet on the structure, and I will leave it for you. Disclaimer. I hope I'm clear with this. Okay, so the last thing I want is I want to select those members. Okay, wait, we selected. Let me just check. We selected those things. We selected those things. Look, my target is to select those things and those things. I want them to be one group. So how do I do that? Well, I select this, and I select this, and then I think I can remove from the selection, right? If I go here and say, well, okay, groups, I think this, remove. Yes, perfect. I have it. Do I have it? Do I have it? Yes, I have it. I will consider this to be the next group. Now, I can give it a fancy name if I want. I just want to show you here. This is this, this is this, and this is this. And finally, I have my chords. This is my, I will call this, I don't know, I'll just rename that. I call this, I don't know, V thingies. And I'll call this truss diagonals. So rename truss diags. And I'll call this truss quads. Truss quads. And say those are like, I don't know, like main chords or something. That's the name. Okay, now I think if my calculations are correct, I should select everything like this. Everything, right? I should go to my selection tool and remove the groups. Let me remove the main chords. So now start doing that here. Let's remove this. Let's remove this. Let's remove this. Did we do that? Yes, perfect. There we go. So that's, oh, wow. I love when things get full circle, because trust me, I have like video edited a lot in this video in terms of grueling task. I don't video edit my errors, but I video edit my grueling tasks because I don't want you to get bored. But those tricks are important. So I will call those horizontal square. Design of connections, design of members, design of foundation will be the topic of next time. It was a grueling task, to be honest. This modeling is more than I thought. Those are my thoughts on it. Furthermore, just heads up, next video will be the finalization of this entire structure. And the structure after this is going to be a silo, a steel or concrete silo. This is where you can add, for example, cement, storage silos, and stuff like that. So there will be a silo. Stay tuned for more. Anyway, trust me, today was, like, I didn't expect this. Now, my thoughts on this lecture are, I thought this would be a joke. Like, I thought literally that it's just going to be an application of forces and that's it. But, and first of all, thank you very much, my dear subscriber, Donald Khani, who basically suggested that I should go into the calculation of those forces. Because trust me, like, you have seen me struggle. Like, there are so many things that can go wrong, and there are so many considerations for the loads, because you need to split the dead and wind alone, because those are two different cases, and those have different factors when you factor the loads to calculate the sections. Yeah, I mean, my video recorder says 57 minutes. Of course, I will video edit a lot of this because I want it to be short and not boring, but it took me much more time than I thought. Also, the selection thing was a grueling task, but now I have those things ready, and I will be using those things in the next video. So I'll upload the structure where you have the loads for your reference, and I will continue talking about the design of the structure in the next video. Anyway, I hope that you enjoyed the video and that it was beneficial for you. Of course, if you have enjoyed the video, then please like, share, subscribe, and so on, especially subscribing because it helps this channel immensely. This is the Civil Engineering Essentials channel, and we will catch you in the next video.